Director of the Virtual Lab, and I'm joined by John Chattel, our Technical Production Manager of the VLab Forum. Welcome for the October edition of the VLab Forum. We're coming to you live from the VLab Forum studios here in beautiful downtown Silver Spring, Maryland, in the shadow of the giant acorn. As always, the VLab Forums are provided as an opportunity to share information about new and interesting research and development that is potentially making its way to weather service operations for the purpose of better preparing weather service operations for that potential new science and technology. The format of the VLab Forum is about 30 minutes of content followed by a question and answer session. We ask that you hold your questions until the Q&A part, unless it's an urgent clarifying question. When we get to the Q&A section and our presenters are have completed their content, we will ask you to raise your hand using the GoToWebinar raise your hand feature to ask a question, and John Chattel will unmute you so you can pose that question directly to our presenter. You can also use the chat feature to ask a question by that method, in which case John Chattel will relay your question on your behalf to the speaker for their answer. A further reminder that this session is being recorded and will be uploaded to the VLab Forum website shortly after the conclusion of the session, so you can share it with your colleagues or friends at your leisure. So without further ado, I'm very pleased to present or introduce our speaker and the topic. Speaker is Barjenbruch. Correct me, Brian, if that is not the right pronunciation. Did I get that about right?
Yeah, I'd say you're pretty close.
All right, all right. From WFO Omaha, Nebraska, is that right?
That is, yep, sunny Omaha.
All right, Omaha. And I believe this is also sort of co-authored by Kris Sanders from WFO Topeka, Kansas. Is that right?
Yep, you're absolutely correct. He couldn't attend today, but he's here in spirit.
Right, great. And the topic is specifically the freezing rain accumulation model, otherwise known as FRAM. And here it is, October. It's cool nights and cool mornings. The frost is on the pumpkin. We've had measurable snow in some parts of the CONUS already. So time to talk about freezing rain, a very challenging problem. So I'm very interested to hear what the FRAM model can do. So take it away, Brian.
All right, well, thank you very much, and thanks for the invitation to present here. We'll go ahead and jump right in, and like you said, we're going to try and hit on the FRAM that we've developed, not only its operational utility, but a few application tips that we've come across, and also our ongoing research on that front, just to kind of give a taste of what's to come. I'm going to lead off with a couple of important definitions and abbreviations. First, the FRAM is the freezing rain accumulation model. We'll just refer to it as FRAM. And another one we'll use frequently throughout this is the ILR, or ice to liquid ratio. That is what it sounds like. It is similar to a snow liquid ratio, where if you have an ice liquid ratio of 2 to 1, well, then you would expect 2 inches of ice for every 1 inch of liquid precipitation. One other thing that I want to point out, and something that we've come across as being important in our research, are differences in how we measure ice. And here is just a quick example, but on the left-hand side, you see we've got 1 inch diameter of ice. That's a ½ inch on each side of, say, a wire or a branch. In the middle, you'd see 1 inch radial ice, a significant amount more than if you've got 1 inch diameter, especially in terms of weight. Or on the far right side, you've got 1 inch of flat ice, which would accumulate on a horizontal surface. Pretty straightforward. The main reason we want to point this out is because currently the NDFD describes ice accumulation as the average thickness on all surfaces. So it's extremely important when we're communicating to our partners what we're forecasting. We want to make sure they have clear expectations of what we're forecasting, because we could say we expect 1 inch of ice, but it's important to be pretty clear on that, as those would be significantly different impacts depending how you're measuring it. For what it's worth, ASOS measures elevated horizontal surface icing, and so that is what the FRAM predicts. The good news is geometry allows us to convert all these very easily. Again, the good news is if you've got a partner who desperately wants to use radial ice thickness for whatever reason, it can be easily converted. But just moving forward, we will be almost exclusively discussing things in terms of elevated horizontal ice, mainly because that's what ASOS measures. So what is the FRAM? Well, it is a statistical, and I want to emphasize that, statistical method to predict ice-liquid ratio. And it is based on more than 1,200 hours of actual freezing rain observations. So why does it work? Well, ILR, simply put, is strongly correlated to measurable and predictable meteorological conditions. And with that said, let's just jump right into exactly what those conditions are. And the strongest correlation to ILR, what we found in our research of, again, more than 1,200 hours of icing, was precipitation rate. Simply put, as precipitation rate increases, ice-liquid ratio decreases. And not only that, but it decreases sharply and, again, has a very strong correlation. So if you focus on this box and whisker, we're looking at precipitation rates of 500ths to 800ths per hour of liquid precipitation, and your mean ILR for that is about 0.75 to 1. You're going to see this frequently throughout the presentation, but ILRs are commonly less than 1. You don't just get the same amount of ice as how much liquid falls. It's very rare, actually, for that to happen, to have a perfect correlation 1 to 1. Back to precipitation rate, so that is for a 500ths to 800ths per hour liquid. You would expect a 0.75 to 1. But once we get into heavier rains, greater than 1700ths per hour, the expectation is actually for closer to almost 0.4 to 1. So if you get an inch of rain at a very high precipitation rate, you're probably only going to see about 0.4 of an inch of ice accumulation. Why is that? Well, basically stated, raindrops are warm, specifically in freezing rain conditions. We have very warm temperatures just above the surface. And in order to freeze, we've got to remove heat, or at least something has to remove heat from those raindrops. Heat removal takes time, and that is the key element when it comes to precipitation rate, because at greater precipitation rates, water does not have time to freeze to the surface before additional water is added. And what ends up happening is that excess water runs off of whatever item it's attempting to freeze to. Now, some of it will freeze because the temperatures are cold, and there are conditions where it will freeze more efficiently. But generally speaking, when it rains harder, more of that water is going to run off. The next meteorological condition that we found to have a good correlation was wind speed. And wind is an interesting element here because it generally, as wind speed increases, the ILR increases. So efficiency of icing really ramps up. You see that especially when we get above 12 or even 15 knots. Now, those are pretty rare occurrences in the general ice storm setup, but you can have very efficient icing. And here you'll notice I highlighted anywhere less than 12 knots, you get a general increase in icing efficiency. But really, when you get above 12 knots and especially above 15 knots of sustained wind speed, that's when you really start to see some of these very efficient icing events. Well, why is that? Two reasons, actually. First, increased wind leads to increased horizontal moisture flux. The physics of the scenario basically just give a greater chance for a droplet to contact a freezing surface in the presence of strong wind. The other reason, once again, I'm going to start with a common theme here. Raindrops are warm, and in order to freeze, we've got to remove that heat. Wind is a very effective mover of heat. It can advect warmer air in, it can advect colder air in, and we're doing this in a freezing scenario onto a microscopic surface. So what we need is air movement. We need that convection to pull the heat away from the surface so that we can have more effective freezing. Especially when you have strong cold wind, and you'll see again in ice storms, a component of cold air advection on the larger scale is very important to having efficient icing in an ice storm. The third and final meteorological element that we found to have a good strong correlation was the wet bulb temperature. And again, generally speaking, to summarize, as the wet bulb temperature decreases toward -2 Celsius, or around 28 Fahrenheit, the ice to liquid ratio increases sharply. Anywhere colder than about -2 Celsius, and it's fairly stagnant. You actually see slightly lower efficiency as you get much colder. To be perfectly honest, there's not a lot of observations down there. Some of that may include some instances of mixed precipitation, although that would be a failure of the ASOS. So generally speaking, once you get below that 1.5 to 2 Celsius of wet bulb temperature, that's your peak efficiency for temperature-wise. And why is that? Oh, sorry, wanted to highlight those areas again. There are a few observations where the wet bulb was right around freezing, actually exactly at 0 Celsius is these 14 observations. But as you get just below freezing, that's where you start to see the increase. And then again, below 1 to 2 Celsius, that's where we really see our maximum efficiency. So the why, well, this one's a little straightforward, but we'll start with the common theme. Raindrops are warm, we've got to remove the heat, and the colder near surface air typically relates to colder freezing surfaces, and things freeze quickly. This is especially true in the presence of wind. But why wet bulb instead of air temperature? Well, wet bulb helps account for evaporative cooling toward saturation. And even if you don't have a saturated air mass, the air-liquid interface right along the edge of that raindrop on a micro scale, that temperature at that location where freezing occurs does approach the wet bulb. This, again, works especially well in the presence of wind, where you can convect and really approach that wet bulb temperature regardless of what the air temperature is. One important finding with freezing rain and temperature to supplement that is that freezing rain commonly occurs with an air temperature warmer than freezing. Not exactly intuitive. In fact, we had to look pretty hard at these observations, but it was actually relatively common for this to happen. But freezing rain rarely occurs with wet bulb temperature warmer than freezing. And by rarely, I mean almost never. So these are scenarios where you may have a temperature of 33 Fahrenheit, a wet bulb temperature of 31 Fahrenheit, and you will have ice accumulation on branches and power lines. That said, while it's possible to do so, freezing rain is not guaranteed if your wet bulb temperature is at or below freezing. So here is a chart. We again looked at thousands of observations in near freezing conditions. And this is the probability of rain versus freezing rain as precipitation type if the wet bulb temperature is at or below freezing. So this is in Fahrenheit, sorry for the unit switch up here, but if the air temperature is 31.5, well, we're going to have 100% freezing rain in those observations. If the air temperature is exactly 32 and the wet bulb temperature is colder than that, then you'll actually see freezing rain about 65% of the time and regular rain about 35% of the time. That can be a variety of factors. And then you see how that adjusts. But we've even had some freezing rain observations at temperatures of 35 or 36 degrees. It's important to note, but it's not a guarantee. Regardless, the wet bulb temperature in these scenarios must be at or below 32 degrees. Let's jump into the FRAM a little farther. Basically, what we do when we're developing this model and using it to predict ice amounts, we forecast those three elements: the precipitation rate, the wet bulb temperature, and the wind speed. We do it on an hourly basis because that's the time span of all of the observations that were analyzed. And we throw them into the FRAM, which basically uses a binned multivariate statistical analysis. I didn't put the equation in here, but if you have any more questions, I'd be more than happy to provide some supplemental information about the details of it. But basically, hopefully that doesn't look like a trash can. I'd like to think it's a little better than that, but we put the information out, and then the output is an ice accumulation map. And I just like to point out in this one that it's a very well collaborated ice accumulation map. Part of that is due to the FRAM being utilized within the forecast builder in Central Region. So something that worked out very well. This is a significant ice storm back in January. And as far as how it played out, where the precipitation and the temperatures aligned with the forecast, the FRAM actually did quite well. That's luckily. I will say that farther east, the temperatures were a bit warmer and the precipitation amounts a bit lighter, so it ended up being lighter amounts, but that's how the forecast works. When we look at the performance and how we really took our research and tried to decide if it was going to work or not, we ended up taking 20 separate freezing rain events that lasted 3 hours or longer, excuse me, and we ended up using the FRAM and other common forecast methods to run a comparison. And here's how it came out. The FRAM, the blue squares are the results of what the FRAM put out for a forecast. Well, this Cold Regions Research Laboratory, their simple model shows up in the diamonds, and just a straight up 1-to-1 ice-liquid ratio forecast method, which was commonly used in the past, shows up as a red circle. You'll notice the dark black line would be a perfect forecast. While the FRAM outperformed the existing methods 85% of the time, or 17 out of those 20 forecasts. Even the instances that it was outperformed by one of the other two models, it was by a small margin. So that was good news. The FRAM had a mean absolute error in these events of only 0.05 of an inch of ice, which when you're down on the lower end of the spectrum in terms of observed ice, that can be a pretty big difference. But the ones we really wanted to pay attention to were when we had more than 0.2 of an inch. And you can see that the FRAM did quite well, although admittedly under forecasting a bit on this very higher end one. And finally, the bias was less than 1/100th of an inch. So all told, a pretty effective method. Bottom line that came out of this is that it's a skillful tool. But is it statistical predictive perfection? No, it's not. I don't know if there is any such thing as statistical perfection. FRAM, what it does is forecast the most statistically likely ILR, when in reality, as you saw in the box and whisker diagrams, there's a range of potential outcomes. And it's important to realize that as the forecaster as well. And so from here, I wanted to jump into some application tips, things we've learned over time, things we've been passing on to forecasters out in the field. Basically, situations for which that statistical most likely scenario can be improved upon. That includes near freezing conditions, variations in droplet size and temperature, elevation, even time of day, and also differences between the air and accretion surface temperature. So for near freezing conditions, I'm going to bring back that wet bulb temperature graph, and I'm going to focus on those temperatures that are warmer than -2 Celsius. And you see that obviously there is a decreasing trend. As temperatures warm, we have less efficient icing. Now, I will say that especially when these slightly warmer end of the spectrum temperatures or wet bulb temperatures are combined with heavy precipitation rates or very warm temperatures aloft, those are situations when the ILR is likely to fall near the bottom of the box and whiskers as opposed to near the mean or median or even the top 75th percent. Again, if you have very heavy precipitation rates or warm temperatures aloft, which was the case last January in some of those locations from like southwest Missouri, for instance, had precipitation rates more than 1/2 inch per hour with very warm conditions aloft. That resulted in very inefficient icing. Something to keep in mind. As far as droplet size and temperature, and we led into this a little bit, if you have a very deep or very warm layer aloft, the end result is going to be warmer drops. And all that means is that you have to remove more heat to reach freezing before running off. On the other hand, if you have a quote-unquote just warm enough warm layer aloft, you end up with relatively cooler drops, and they'll more efficiently freeze once they hit that surface near the ground. Excuse me. Similarly, if you have a larger drop size, that allows more capacity to hold in that heat versus a smaller drop size, like a drizzle, for instance, will more quickly freeze to a surface. And on that note, supercooled droplets, for instance, in fog or drizzle, they will freeze almost immediately. And these are scenarios when you can actually have extreme ice-liquid ratios, greater than 3-to-1 and even much higher than that at some times. There have been documented cases of multiple day freezing fog and freezing drizzle events that have caused really high-end electrical towers to collapse due to the weight. Well, very little liquid precipitation accumulated just the perpetual freezing of supercooled drops added up over time. Another thing that I found very interesting, even when down in Kansas, was that minor differences in elevation can play a huge role in icing. You'll notice on our typical ice storm sounding here, in the lowest few hundred feet, you actually have temperatures that cool with height. And as we get closer to that -2, -3 Celsius, keep in mind that's where our maximum icing efficiency resided. Furthermore, as you continue to go up, you obviously warm very quickly with height beyond some point. Well, in a vertical temperature profile that's typical of freezing rain, icing efficiency is going to change based on that elevation. Again, that efficiency will initially increase with height and then become much less efficient into the warm layer. These are scenarios that I'm sure that folks out, say in New Hampshire, Vermont, or out in Oregon, definitely see these. And you can probably literally see them on the hillsides in the perfect conditions, where you may see a stripe of very efficient icing on the trees. What was interesting in Kansas last January, once again, was that over an elevation change of about 200 feet, you could physically see the difference in the amount of ice that accumulated with very similar precipitation amounts. Then, of course, we've got diurnal variations. This one is quite simple, but it was interesting that our observations we grabbed, they showed that during the day, especially once you approach the maximum shortwave solar radiation, icing is less efficient and actually just less likely to occur from a freezing rain standpoint. And finally, differing air and surface temperatures. This is somewhat common sense, but it happens more often than you might think. Basically, if you have a colder surface, it's going to be more efficient at removing that heat and promoting a quicker freeze of the liquid. There are actually times as well where you could have an air temperature of, once again, say 36, but maybe it was a very cold morning, and so your roads are only 29 degrees, or even your power lines and tree branches haven't warmed above freezing yet, so you still get freezing rain. These are important considerations, and they can work in the reverse as well if you have a very warm surface, although air temperatures might be sub-freezing. Now I'll go ahead and jump into some of our ongoing research and related projects. Excuse me, I need a drink of water there. For starters, we're working on some FRAM enhancements right now, almost a FRAM version 2, if you will. We gathered 2 more winter seasons worth of data. This will effectively double the size of our data set. And what that does is it's going to increase the statistical strength. It should allow us to jump into some smaller binned analyses and perhaps change our methods of how we can utilize this to maybe show a more likely range of possible outcomes for very specific conditions. We also hope to include an element of vertical temperature profile as we're going. Again, this is in the process of updating right now, but again, trying to evaluate the temperature of those raindrops aloft and as they're hitting the surface could help us to better predict freezing rain efficiency. Overall, we're just looking to take what is a good forecast method and make it better. One study of particular interest is kind of merging the FRAM into an impact study with a goal of better predicting electrical outage impacts before they occur. We know that as the National Weather Service, we can be very good at predicting ice amounts. We can be very good at predicting other elements like wind speeds, temperatures, so on and so forth. How can we use that in an impact way to work with, for instance, Department of Energy and some of their related entities who they've brought in out of the Oak Ridge and Brookhaven National Laboratories and even FEMA. Basically, they have a historical outage database, which we hope to leverage in combination with our observation database and try and build something with a strong predictive element to it as far as pre-positioning resources and almost predicting impacts before they occur. I realize this is difficult to do, and it's in the early processes, so it's something we're working on with them at the moment. And here's just an instance of freezing rain down in Hutchinson, Kansas. You'll notice the power outages are plotted in blue. The total ice accumulation in a radial number is plotted in pink, and then the wind speed in brown. First thing I want to draw your attention to here is the instance of first power outage, and that's when the radial ice accumulation approached to about 27/100ths of an inch. The next point I'd like to draw your attention to is when we hit about 10% outages, and that is a rough descriptor of when you're getting into significant ice storm scenario. At that time, we actually had a little more than 45/100ths of an inch of radial ice accumulation. And I should note, some of these numbers are very high before we're getting to the higher outages. Hutchinson in particular had a major ice storm mitigation effort, which helped them significantly, as they'd had a major ice storm a few years before this. That said, at these two observations, the wind speeds were light as the ice was piling up. And so now I'd like to draw your attention to a third point, and that's out here where the ice accumulation had stopped and had been done for several hours. But a cold front came through and the wind speeds rapidly increased to greater than 20-knot wind gusts. At that point, we see a significant spike in power outages, up to more than 30% of the population in that area being without power. That is significant because we did not have any additional freezing rain accumulation, and yet we did manage to have a significantly greater number of power outages. And it goes to show something that, again, is in this highly simplified model here, bordering on common sense, but as ice amount increases and as wind increases, you tend to get greater impacts, specifically on the power grid and on trees. That's something that we're going to keep working toward with those partners, and again, hopefully have some results here within the next year or so. Other projects and partnerships, we've been working closely with the Weather Prediction Center with their icing amounts on the winter weather desk. We've had discussions with developers for the National Blend of Models, and then also the FRAM is fully incorporated into Forecast Builder. We also hope to have some discussions, at least at some point, in establishing clarity in what type of ice measurement we're forecasting. Again, you remember from that second slide there, the communication element of this is pretty substantial, and we want to make sure we're all on the same page. Also, it would be interesting once our impact study progresses further to potentially look at a enhanced way of issuing ice storm warnings that may incorporate some other elements beyond simply the icing amount. As far as available tools, I did want to point this out for anyone interested. There is a GFE procedure and smart tool set available. I know several offices out across the country have been using it. It's called the FRAT, or Freezing Rain Accumulation Tool, and it is available for local download. It does require a bit of training and practice. Maybe the most important thing here is that the version within Forecast Builder is quite a bit more sophisticated. It's a very sound version. It's not that the science is any different, but the way that you are predicting precipitation type is a fair amount different. So food for thought there. The FRAT does not supplement the Forecast Builder in any way. I included a few links right here. There's a VLab project link that's out there. It's got a few references on it, as well as a group who have been evaluating it loosely. Also, the FRAT download link from VLab is available there as well. And then finally, just a link to our published paper in weather and forecasting in case anyone is interested. But otherwise, that's actually all I've got for this point. Excuse me, I'm more than happy to answer questions, and I appreciate you all listening in.
All right, Brian, thank you very much. Really great overview. So while you grab a drink of water there, something I'll ask that folks on the line in the GoToWebinar, if you'd like to ask a question to Brian, please use the raise your hand feature, and John will unmute you, or use the chat. So while I'll start it off, Brian. So I understand, thanks for walking us through, the factors involved, precipitation rate and the temperature and the wind speed. But how is the vertical thermal structure taken into account here? Because I'm asking myself, what about ice pellets and the other types of and snow and all that? How does this kick in if you in the FRAM? Is the FRAM only invoked when you have the right thermal structure to support freezing rain, or is it accounted some other way?
Great question, and I actually pulled out those slides in interest of time. FRAM is only for freezing rain, and of the 1,200 hours of observations that we grabbed, we only allowed 60-minute periods of continuous freezing rain, and we gathered all of the 5-minute ASOS observations to verify that only freezing rain was being reported. So that's another thing is what I'll point out there. Within the forecast builder, that's where you get a probability of freezing rain versus a probability of sleet or probability of snow, which can help enhance the forecast based on precipitation type alone. The FRAM itself, though, as you said, is for purely freezing rain prediction. It will work best when the majority or all of the QPF in a given hour is devoted to freezing rain. When you start to get mixed precipitation, obviously that icing efficiency will fall off, but those observations were not included in the data set.
Okay, so in other words, that you can run the FRAM and get an output, but you're operating under the assumption that there's a high probability of freezing rain, and if there is freezing rain, this is the amount you could expect. Is that the way it works?
Yep, absolutely. And within the forecast process, it only adds freezing rain to the forecast where the forecaster's weather is specifically freezing rain. So it's kind of a smart way of doing it within our forecast structure of GFE. But yes, if we should be wrong in that precipitation type assessment, then our freezing rain amounts would obviously be off too.
Okay, so is this being used, across central region as the go-to way to produce that forecast, or are there other techniques that are used?
Nope, as of now, it is, I believe, the primary and/or only way that central region offices are using it to at least create a starting point of freezing rain amounts within the forecast builder context. So the FRAM is being used almost exclusively. Now, of course, like we said, there are situations when you can improve upon it, and those are situations when the forecasters are tasked to collaborate and make those adjustments as necessary.
Okay, great. So what about the other regions?
As far as I know, we've got about a dozen offices across the country. I don't believe any in Alaska, who have downloaded the FRAT tool just for their local use. That number may have changed over the past few months. I haven't gone and checked recently. Otherwise, any offices, I'm unsure of the status of other regions and offices in terms of using the forecast builder, which that would have FRAM automatically incorporated. But as of now, what I can say confidently is central region plus approximately a dozen additional offices have access to it or are using the FRAM exclusively.
Okay, great. So I'm going to use my host prerogative here. John, could you unmute Jeff Wallstreicher for a second? He's sure. Eastern region, and let me ask Jeff a question. If he's on, Jeff, are you there? Jeff. Okay, then let's try Ken Johnson. Let's see if Ken's there. I'm trying to get an Eastern region person here. Let's try Ken. Maybe he's there. Ken, are you there?
Yeah.
Okay, Ken. So how does the Eastern region? What are you guys doing for freezing rain accumulation?
There's a variety of tools. FRAM being one of them. I don't have an exact number off the top of my head here as to who's doing what, but I think probably a fair number of offices are using this FRAM approach. Probably through the FRAT tool. We don't have but one or two offices right now doing a forecast builder.
Okay, thanks, Ken. I see Jeff. Did you want to answer through chat?
Yeah, Jeff may have additional information there.
Okay, Jeff, if you do want to answer, we will watch your chat box there. Okay, other questions, folks? Use to raise your hand. In the absence of some, I'm going to go proceed myself. So I didn't quite understand this, Brian. Like, so you say this forecasts the ILR, but you produce accumulation from that. So is that done within the statistical multivariate analysis? That wasn't quite clear to me.
Yep, sorry about that. Great question. So we are using the FRAM to predict the ILR, but then the ILR is essentially multiplied times the precipitation forecast for that hour. So for a 2-hour period, if an inch of liquid is in the forecast for each of those hours, and the FRAM predicts an ILR of 0.5 to 1 followed by a 0.7 to 1, then we would expect a half an inch of ice in hour 1, 7/10 of an inch of ice in hour 2, and so on. It's very similar to some of the more recent methods for predicting snow amounts. It's done in the background of the FRAT and Forecast Builder FRAM tools, basically looking at creating the ILR grid for all of the grid points across our forecast, and then multiplying that times the forecast precipitation grid. Hopefully that explains well or answers your question.
It does, and so I got, that's a nice way to do it, because that if the forecast is good, you can claim success from the FRAM. If it's bad, you can blame it on the QPF, right?
Absolutely, but nobody would ever do that.
Okay, all right, I'll take your word on that. So Jeff Walstreicher did reply to chat, and he says he doesn't have much to add, but WPC is utilizing a version of FRAM and that goes into their ice accumulation probabilities. Okay, thanks, Jeff. Appreciate that. Any other questions from the webinar, folks? I don't see any yet. So this is a little bit more just curiosity thing, Brian. So do you know what percentage of the outages are due to tree branches falling on lines versus just lines going down themselves due to weight and or wind?
Another very good question. That would be more in the lines of Department of Energy. Our contacts there, I'm sure, would have a better feel for it. What I have seen personally in the past, a very high percentage is due to trees. In that specific example I showed of Hutchinson, Kansas, not exactly known for its tree cover, the mitigation efforts that they went through strictly from a tree standpoint basically reduced their outages by almost 35% in a nearly identical ice storm. So trees are a huge role. I will say that when the wind starts to become more of a factor, that's when, well, you'll see in the bottom right and bottom left images on my thank you screen here. Those are instances where you can get galloping lines, where the resonance frequency can become just perfect, that essentially everything comes down. There are scenarios where the weight just overwhelms it too, but for the most part, the Society for Civil Engineering has set some pretty strict standards for building those power lines in relation to ice, and the Krell model that we compared our results to is actually related to that civil engineering criteria. So I'm rambling at this point, but bottom line, I believe trees are a significant factor, and that's actually an element we want to bring in to our impact study with the folks from Oak Ridge National Laboratory and their mapping data sets of primary vegetation and tree types. Okay, yeah, that makes sense. A few years ago in the DC area, PEPCO, the local electrical utility, went through a major mitigation thing as well, and it was basically removing, clearing tree branches from overhanging power lines, that sort of thing. So that jives completely with your observation. Another one for you. So has this sort of approach been applied to try to do like a radar-based freezing rain estimate?
like not a forecast, but like a real-time thing.
As far as I know, it hasn't. That would be interesting, just to pull in real-time observations and kind of fill in the gaps in between our ASOS network of ice observations. Yeah, that would be interesting, especially from a nowcast perspective.
Right, because you'd see, so with the dual pole, you could get some idea about the drop size. You have the precip rate, presumably you can get the winds and your other information. So that I'm surprised that that hasn't been applied yet, but you never know. Maybe we're just not aware of it.
That's true. It could be being done as we speak.
Right, right. All righty. Do we have any other questions from the folks on the line?
Hey, Steve, I've got a quick one for Brian.
Go ahead.
So, Brian, what is the path to operationalize the FRAM? Is it strictly through the forecast builder, or is there some other mechanism that it might find its way into national-wide use?
You know, that's a good question, and one that we've posed a few times to folks regarding FRAM, and then also, as we mentioned, some of the descriptions of ice that we're measuring, ice storm warning criteria, things like that. I would say that as of now, Forecast Builder is probably, I will assume, spreading it at such a rapid rate that might be the way that it first is distributed. Across Central Region, FRAM was used because within Forecast Builder because it worked better than what was out there already, which is one of the reasons that we're trying to continue to improve, not just to sit on it and call it done. It will be interesting to see how this progresses, to be honest. Kris and I are very much in for making it the best method out there and trying to spread it to folks to improve those ice predictions, but typically things spread based on how well they perform. So as of now, I'd say Forecast Builder is really getting it out there, but I don't know. Perhaps someone on the call would have a better feel for it than I even would.
All right, thanks.
Another one, Brian, I've got, this is Steve Smith again. So obviously you get freezing rain in Omaha and the et cetera that you deal with during the winter season, and you're highly engaged in improving the forecast of it. So what do you do on the decision support side of things when FRAM's showing you kind of like a potentially bad freezing rain situation? How do you engage your core partners to prepare and et cetera for that potential?
Well, we use a series of basic outreach materials. We've got PDF briefings that we'll send out frequently to email lists. As confidence increases, we will often use webinars. Mapping resources are used to illustrate where those greatest risks are. Not only that, but we use some of that impact-based information as far as what sort of icing amounts tend to lead to tree damage in the absence of wind or incorporating wind. Mostly it's doing what we can from a communication standpoint to get it out there. And the main way that we do that here, and the main way we did it in Topeka when I was there recently, is basically through massive efforts of communication, one-on-one with those partners who we know, the partners who trust us locally, and that tends to get the best results.
Okay, great. So the other aspect I know of this problem is that there are these sort of stealthy kind of freezing rain events, which they don't show up very nicely in the general forecast, but you get just the right conditions and a stray radar echo dropping a little bit of precip on a major artery, you can have a huge impact, right? So those ones are trickier to anticipate, I presume.
Absolutely. Freezing drizzle is one of my worst enemies. It's extremely efficient, especially when you have cold roadways. and often the drivers in particular can't tell when wet turns to ice, as we're all familiar with. Those are the scenarios that, again, they don't lead to major ice storms, but they do lead to major impacts. And that's something, especially in the winter walk warning operations course that we just helped to build a module for, we try to emphasize that it's messaging in those events too. It's not just the major ice storms that will get you, but on those days when you do see 2/100ths of an inch of rain coming and they're going to freeze, it's worth spinning up those decision support resources to send out to the rest of all your partners. Even if it's just an hour or two in advance, it can be useful.
So relying on your legacy toolkit of watches and warnings doesn't cut it for that sort of thing. You really have to engage the partners, ahead of time. Is that what you're saying?
From my personal perspective, absolutely.
Yeah.
You can issue an advisory, but it's what gets said with the advisory, what is translated from us to the media and from the media to the world, and what's translated from us to those key partners so they can prepare for it. Department of Roads, Emergency Management, and Public Safety. You're absolutely right. That is safe to say.
Because we don't have a freezing rain emergency, to issue, right?
No, we don't. And I don't know what we'd do necessarily with a freezing rain emergency if there was, around a freezing drizzle coming at rush hour. But we can't communicate to the masses in a super efficient way. We know people who can, that being the media.
Right.
So,
right.
Yep. Yeah.
Okay. One last call for questions on the webinar. Well, seeing none, I want to, we'll conclude. And I want to thank you, Brian and Kris, out there, pass along our thanks for his contributions here. Really informative talk, one we haven't seen, I think, ever in the VLab Forum. And so this is good. And it's another great example of, the innovation and creativity of the field folks in Weather Service, solving their own problems, helping out everyone else. And I'm great to see you using the VLab to share your techniques and your progress so the benefits can be spread throughout the Weather Service in due time. And part of that is getting on here and giving us an update on all of it. So really want to thank you. And anyone who wants to follow up with Brian, you can get him by email. We will maybe be hearing more in the future about the expansion of FRAM to national implementation, maybe with the blend or something like that. So, alrighty, with that, thanks, and we will conclude. And again, John will send out a heads up when the recording is finished and uploaded to the VLab Forum website. And what do we got coming next month, John?
Let's see, we've got a high-resolution communication analysis of the integrated warning team during the 26 December 2015 Sundale, Garland, Rowlett, Texas tornado.
Yes.
By Dennis Kavanaugh.
Dennis Kavanaugh from what office? Arizona?
I don't know.
Okay, I forget what the office is.
Oh, in Texas?
Yeah,
Little Rock, I believe.
Little Rock, right?
Little Rock.
That's right. So he gave this talk at NWA, and it was really great. So we've reached out to him, and he's going to do a encore presentation just for the VLab Forum on that. A lot of cool stuff about communication during tornado outbreaks, IDSS, and network analysis on communications. So that I really encourage folks to dial into that one next month. So, all right. Thanks, everyone. See you in November.